Okay, that on our previous lesson we have learned kinematics of material point, and now we have to learn kinematics of perfectly rigid body that rotates around the fixed axis. Perfectly rigid body is a system of material points which cannot change, which cannot change their positions related to each other. So this is a perfectly rigid body, or solid body, in other words. So let's have a look at a coordinate system. We will sign axis of rotation as axis z. Here we have some rigid body. It may have any form. It may have any form and three axes: x, y, z, and axis of rotation is axis z. Axis z is axis of rotation. This is axis of rotation, and the direction of rotation is here. This is direction of rotation around the axis z. It is, I think, it is obvious that every point of rigid body will move along a circle. So trajectory of each material point will be a circle. So let's I'll draw schematically this circle. I will draw this in such way. This is trajectory of some material point of rigid body, and as it was on previous week, we can define radius vector of material point. In first position, it may be r1, and in its next position, it will be r2, in its next position, and we can also define a radius vector that begins in the center of this trajectory, in the center of this circle. We can define this in such way. And we will sign it as R2, capital letter R, with capital letter R. I will make it bigger, and here R1. And here we have some angle of rotation, some dphi, and displacement vector. Displacement vector can be shown here, and it is equal to dr. dr. dr is displacement vector. Is displacement vector. Okay, and according to this picture, and according to theories that we have learned before, we can say that absolute value of displacement vector. Now we consider infinitely small displacement vector, and for infinitely small displacement vector, absolute value of this displacement vector, absolute value, I will write this in such way. And from our previous week, we know that it is equal to path length. Path length is ds. ds, where ds is this part of circle. This part of circle is equal to ds. Is equal to ds, and we know that it will be r. Will be r multiplied by angle of rotation dphi. Change of angle of rotation dphi. What is r? R is absolute value of R1 and R2. Of course, we can write that absolute value of R1, and it will be equal to absolute value of R2, because radius of this circle change its direction, but doesn't change its absolute value. So absolute value will be the same, and we can write it as r. But the same will be with these radius vectors. The same will be for this radius vector r1 is equal to absolute value of r2, and this is equal to r. This is equal to r. This is equal to r. Because small radius vector r rotates along a cone. Okay, so what can we say? What can we say about the connection between capital R and small r? We can rewrite this picture. In some cross section. So we can redraw this picture again. Redraw this picture again. I think I will make it just a little bit bigger. And axis z. This is the same axis z as here. The direction of rotation is here. And here we have origin O, and radius vector r, small letter r, will be here. will be here, and big letter R will be here. So it is just a cross section of the picture that was shown above. So we can notice that this is a right angle, and here we have some angle alpha, and it will be R. Here will be R, and here will be small letter r. And from this triangle, we can notice that capital letter R is equal to R multiplied by sinus alpha. Multiplied by sinus alpha. Multiplied by sinus alpha. Okay, and we can substitute this formula in here. We can substitute here this formula, and we will have that this is R dφ, where dφ is increase of angle of rotation, and multiplied by sinus alpha. Okay, do you have any questions about this?
So far, so good. It's clear.
Okay.
Oh, thank you.
Okay. What can we say about the direction of vector of velocity? The direction of vector of velocity. If the rotation is the direction of rotation is here, this material point will move from us to the screen on this picture. It will move from us to the screen. So we can write that a vector of velocity will be perpendicular to the screen and directed from us to the screen. And it can be signed in this way. Here we have the vector of velocity. Of course, on this picture, above, it will be somewhere here. Vector of velocity. Vector of velocity is always tangent to trajectory. It is always tangent to trajectory. And what about the absolute value of vector of velocity? We know from previous week that absolute value of velocity v is equal to derivative dr divided by dt, and as we can notice from this picture, r and sinus alpha are constants, and the same is for small r. So we can write that r dφ divided by dt and plus it is equal to r dφ divided by dt sinus alpha. And what does what does this derivative mean? What does this derivative mean? It means change of angle of rotation. Change of angle of rotation in time. Change of angle of rotation in time or velocity of this change of angle of rotation. And this value is known as angular velocity. Angular velocity. Let's define this. So angular velocity. Angular velocity. Absolute value of angular velocity is equal. This is absolute value, and this is equal derivative from angle of rotation, dphi by dt. Now this is angular velocity. This is angle of velocity. And the question is how to define the direction of this vector. Because here we just define only its absolute value. So how to define its direction? It can be defined according to right hand rule. So if we draw here the right hand, and when these fingers show the direction of rotation, this finger some finger will show the direction of vector omega, the direction of angular velocity. So angular velocity will be here, and it means that on this picture the direction of angular velocity will be here. So this direction is the same as the direction of axis of rotation. And it is necessary to say that if we have another direction of rotation, for example this, if we have another direction of rotation, we will get another direction of omega according to right hand rule. But now we have just this, and on this picture we can also write this vector of angular velocity. It is here. So according to this new definition of angular velocity, we can rewrite the formula above in another way. We can write this as v is equal to omega r, and this is equal to omega r sinus alpha. And how to write this in vector form? how to define this in vector form. According to vector algebra, it is possible to prove that to satisfy the directions of this on this picture, we can rewrite this formula in vector form with vector product or cross product. Vector product is the same as cross product, so it may be written as omega multiplied by r, vector product or cross product. And here we have omega multiplied by r. So this is a vector formula. And this is vector formula. Okay, so do you have any questions about connection between velocity, angular velocity, and radius of rotation?
Nope. Okay, it's okay for me.
Okay. So I will frame this in red. Because these are important formulas that we will use tomorrow to solve some problems. So it is a connection between velocity and angular velocity. A connection between velocity and angular velocity. It is here. Okay, what else can we say about this? We know from previous week that velocity may be also changed in time. Velocity may be also changed in time, and in the same way that it was made by velocity, we can make this with angular velocity. So we can define angular acceleration. Angular acceleration. It can be signed as beta. Beta is equal to derivative d omega dt. This is angular acceleration. Angular acceleration, and in the same way as it was made before, we can define connection between acceleration, angular velocity, and radius vector. So we can define acceleration of any point of rigid body. Or solid body. This is the same. So we can define this in a way that is very similar that is very similar that we used to get this formula. The way is very similar, but we have no enough time to dive deeper in this. But in short way, we can say that tangential acceleration, I mean its absolute value, can be defined as angular acceleration multiplied by r. And this is the same as beta r sinus alpha. Beta r sinus alpha. You can see that very similar formula to this, the formula above, very similar. Angular acceleration. Angular acceleration. The next is, we know that we have also normal acceleration. From our previous lesson, we know that normal acceleration can be defined as squared v divided by r. So we can use this formula here, and so it will be omega r to the power of 2 divided by r, and it will result as omega to the power of 2r, or it will be the same as omega squared r sinus alpha. So this is normal acceleration. This is normal acceleration. This is normal acceleration. I remove some temporary formula, and normal acceleration. Normal acceleration and the full acceleration, or just acceleration. We know that its absolute value is equal to, according to Pythagoras theorem, it is equal to square root of squares of tangent and normal accelerations sum. So we have this formula for full acceleration, and according to formula above, it will result r multiplied by square root beta to the power of 2 plus omega to the power of to the power of 4. Of course, because here we have omega to the power of 2, and to the power of 2 again will result to the power of 4. Will result to the power of 4. So is full acceleration. Or just simple acceleration. It is full acceleration. Okay, and it is necessary to say a few words about where kinematics can be used. For example, kinematics can be used some software and some drivers for computer mouse. I mean that to code drivers for computer mouse, it is necessary to calculate and define the connection between kinematics of computer mouse on its pod and the connection between and connect kinematics of computer mouse on mousepad with kinematics of it on the screen. So we can connect motion of cursor on the screen and motion of mouse on mousepad. And here in this question we can use kinematics. And because of this kinematics may be useful for us to do this. And of course, in computer games, in some computer games, this kinematic formula are must have to define some motions of object in computer games. Okay, do you have any questions?
It's okay.
Okay.
Mhm.
Okay, so let's start a new topic. And it will be dynamics. As you can remember, in kinematics we consider only mechanical motion without any factors that may affect on it. But in dynamics we take into account some factors that may change motion, that may have influence on velocity, on the direction of velocity, and it may influence on motion. And so we take into account these factors in dynamics. The basics of dynamics are three dynamics laws. Three laws of dynamics, or they are also known as Newton's law. And the first law of dynamics, is Newton's first law of motion. Maybe I will write this. Newton's first law of motion. So let's I think Newton's Newton's first law of motion. Newton's first law of motion. According to this law, every body continues in its state of rest, or of uniform motion, uniform means that motion with constant speed. Uniform motion in a straight line in a straight line, unless it is compelled, to change that state, change that state, by forces, impressed upon it. Force is a value of interaction between objects in mechanics. The value of interaction of objects in mechanics is known as force. And a system where Newton's first law of motion is true is an inertial system. Inertial system is a reference system where Newton's first law of motion is true. But according to this law, we can see that if there are some forces, they will make some effect, so they will influence on our motion. So we have to describe this influence. In some way. So how to do this? First of all, it is necessary to define a new physical value. That known as momentum. Momentum is just a scalar product or just simple product of mass and vector of velocity. So momentum is equal to mass of material point or body and its velocity. You know that mass is a physical value that is in kilograms. Velocity is in meters per second, and it means that the momentum will be in kilograms multiplied by meters per second. So this is momentum. And here we have to say about the second Newton's law. It results from experience, from experiment, or the many experiments and observations during a few centuries has shown that change in momentum. The change in momentum is equal to force. Impressed upon material point on body. And this is known as Newton's second law of motion. 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 According to this law, derivative from momentum with time is equal to force. Force is a physical value that is in newtons. Newtons is unit for force, and this force describes value of interaction between objects in mechanics. So it can be written in this way, or it can also be written as according to this formula. It can be written as dmv divided by dt, and this is equal to force F. So it is necessary to say that if we have not only one force, but if we have a few forces, it is necessary to consider their vector sum. So in this case, F will be equal to, if we have a few forces, F will be equal to some vector sum of these few forces. If we have not one force, but if we have few forces, so it is necessary to consider their vector sum. And of course, Newton's second law of motion can be defined in verbal form. The change of momentum P, the change of momentum of an object, is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. But I think it's simpler to use formula in this case than verbal definition. And in most of the cases, we have the situation when m is constant. So if m is constant, we can say that we can rewrite Newton's second law of motion in another way. If m is constant, we have that ma is equal to F, or we have so here we have vector, of course. A is acceleration, that is first derivative from velocity, dv divided by dt. Or we can write this as m dv divided by dt is equal to F. Or what is the same, What is the same? What is the same if we remember that v is equal to derivative from radius vector, we can say that it will be m, and here we have second derivative from r by dt 2. This is second derivative, and so all these formula are equivalent. All these formula are equivalent. Okay, and now as you can see, we have in second Newton's law of motion, we have physical value that is known as force. And so it will be useful to do exercise. It will be useful to say a few words about some forces that we can often meet in some practical cases. Some forces that are important for practical cases, and the first is elastic force. Elastic force. This is the first type of force that we can meet in some practical cases. Elastic force in simplest case. I will draw a picture. So here we have some fixed wall. This is some fixed wall or fixed base connected to some spring. This is spring, and this spring connected to rigid body. This spring connected with rigid body. And let's consider some elongation or extension. Of the spring. Let's consider some elongation or extension of the spring. Elongation that we will mark as x. Of course, it will not be easy to elongate the spring because we have elastic force. We have elastic force in the spring that try to prevent the spring from the elongation or extension. This elastic force in simplest case may be defined as F is equal to T x, where key is a spring constant. Key is a spring constant. Spring constant. This is a spring constant is a characteristic of the spring. Characteristic of a spring. It depends on its form, on its shape, and its material. And this formula defines elastic force in the simple case, and this formula is known as Hooke's law. This is Hooke's law. Hooke's law. This formula is Hooke's law. And sign minus means that elastic force is tried to prevent spring from extension. Extension or in general case deformation. Okay, do you have any questions about
Nope.
Hooke's law?
I remember from high school. It's okay for me?
So you remember this from
Yeah, part of the topics, yeah. Part of
That's
topics.
great. That's great. That's great. It means that you had a good school. You had good school, and you have studied well in it. So in some exercises, it is necessary to calculate mechanical strengths or tensile strengths. What is this? Let's define this tensile strengths. Tensile strengths. Tensile strengths. Let's consider a homogeneous rod. Simple homogeneous rod. And when it is non-deformed, it has length. It has length equal to L. When this rod is not deformed. But if we put some extension, in this case we will mark this as delta L. Delta L is a extension. It is extension. And if we use Hooke's law for extension of this rod, we will get that F. But now I will write absolute value of elastic force. It will be spring constant multiplied by delta L. We have written delta L instead of X. And it can be rewritten in another way. K L multiplied by delta L divided by L. And to get tensile strengths, to get tensile strengths, we have to divide force by area of cross section of the rod, by area of cross section. So tensile strength is equal to F divided by S, and this will be equal to K L divided by S, EL divided by S, and here d delta L divided by L divided by L. And we can rewrite this. We can rewrite this as E multiplied by absolute value of epsilon. Absolute value of epsilon. Now I will explain. Here we have got another form of Hooke's law. Another form of Hooke's law. Another form of Hooke's law. So we can write that this is also Hooke's law. Hooke's law. This is also Hooke's law, and here we have sigma is equal to F divided by S, and this is tensile strength. Tensile strength. Tensile strength, and E is equal to KL divided by S, is a Young's modulus. This is Young's modulus. Young's modulus, and the last value is relative elongation or relative extension. So epsilon is equal to delta L divided by L is relative elongation or relative extension or relative extension. So this is so these values are in Hooke's law for this rod. Hooke's law for tensile strength. This is another form of Hooke's law. Sometimes it is necessary one form, and sometimes it is necessary the other form of this. Sometimes it is necessary the other form. Okay, and the next force that we will learn is force of gravity. Force of gravity, and according to it can be calculated. It can be calculated from Newton's law of universal gravitation. 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 Let's consider some two bodies that have form of spheres of balls, and its density distributed symmetrically in relation to their centers. So the first body has mass m1, and the second has mass m2, and the distance between their centers is r. The distance between their centers is r. And in this case, the interaction between these two mass is defined by gravity force, and this gravity force is equal to g multiplied by m1, m2 divided by r to the power of 2. And this is gravity force. Is force of gravity, or gravity force. Force of gravity. And g is a fundamental constant. G is equal to 6.673 multiplied by 10 to the power of minus 11 newtons on meters to the power of 2 divided by kilograms to the power of 2. Kilograms to the power of 2. This is gravity constant, or gravitational constant. Gravitational constant. Is gravitational constant. This Newton's law of universal gravitation. It allows us to define a force of gravity between two bodies with masses m1 and m2. Okay, and let's define force of gravity. For body near the surface of our planet Earth. In this case, we have that force of gravity will be equal to g mass of body, mass of our planet Earth, ME, mass of Earth, divided by R, where R is radius of our planet, to the power of 2. And if you found in the internet mass of Earth and radius of Earth, and calculate and make some simplifications, we will get that it is equal to mg. Where g is acceleration of free fall. Acceleration of free fall that, according to formula above, is equal to gme divided by re divided by re to the power of 2. To the power of 2, and it is approximately equal to 9.81 meters per seconds to the power of 2. This is acceleration of free fall. Acceleration of free fall. Okay, do you have any more questions?
Nope, it's okay.
No, thank you.
Okay. Okay, and the last important force for exercise is force of friction. Force of friction. So let's consider some rigid body on a rough plane. On a rough plane. On rough plane. Here we have rough plane. Rough plane. Rough means that it is not flat, smooth. It is not flat and smooth. It is rough, and rough means that there is interaction between this surface and body upon it. So here we have body on surface, and of course we have force of gravity. Force of gravity is impressed. Force of gravity impressed upon body. Force of gravity, and on our planet we know that force of gravity is equal to mg. Force of gravity is equal to mg. But as we know that body on this plane will not fall down. And according to the first Newton's law of motion, it means that there is some force. There is some force that compensates force of gravity. It compensates force of gravity, and this force is force of normal reaction. Force of normal reaction. It is some force n. Force of normal reaction. Force of normal reaction. N. Force of normal reaction. And of course, we can notice that this force n, is equal to minus mg. because in another case, our body will fall down or take off of the plane. So if we don't have these cases, so we have equation here. We have equation, and if this body moves to the right, with some velocity v. If it moves to the right, and if the surface is rough, force of friction will occur between the body and the plane. Force of friction will occur. Force of friction, I will sign this as F. Force of friction. And this force of friction may be defined according to the law of friction, the modulus of force of friction may be defined as mu multiplied by absolute value of normal reaction. Where mu is coefficient of friction, or friction coefficient. Friction coefficient is friction coefficient. So force of friction. So here, where all forces that we need to solve exercises effectively. And but these exercises for dynamics will be later. Tomorrow we will do access for kinematics, and only in 2 weeks we will have exercises for dynamics. So here the all forces that we need. And what else is necessary to learn today? Let's consider some material system that consists of two material points. The whole momentum of this system is equal to sum of momentums of these two material points, P1 plus P2. P1 plus P2. P1 plus P2. P1 is momentum of first material point, and P2 is momentum of the second material point. And let's consider the situation when there are no external forces impressed upon these material points, but there is interaction between them. Interaction between parts of the system, between parts of the system is known as internal forces. So we have only internal forces, but no external forces. So in this case, we will have that derivative of momentum of material system. This derivative is equal to derivative of first momentum plus derivative of second momentum and it will be equal to zero. According to second Newton's law of motion. We have zero in right side of the equation because we don't have any external forces. This is important in this case, that we don't have any external forces, but we have internal forces. We have internal forces, and for these forces we can use this formula also. We can use this formula, and for them we have this is F1, 2. The force, internal force impressed upon point 1 and that acts from point 2, and in the same way we can define force F21. Force internal force that is impressed on point 2. And from here we get that F12 plus F21 is equal to 0. And from here we get that F12 is equal to minus F21. Is equal to minus F21. And it is possible to prove that this result will be the same for systems that consist of any number of material points, and for each pair of internal forces we have this relation. So for each pair of material points, for each pair of internal forces, I will change indices 1, 2 into I key to notice that this is universal relation, and this relation is a partial case of third Newton's law of motion, or Newton's third law of motion. So Newton's third law of motion, Newton's third law of motion, can be written as such relation. Newton's third law of motion. here. Of course, it can be described verbally. In words, it will be definition. To every action, there is always opposed and equal reaction, or the mutual action of two bodies upon each other are always equal and directed to contrary paths. So this is definition of this formula in words. But I think this mathematical definition is more useful. And more clear. Okay, do you have any questions?
Nope. Sorry. It's okay.
Okay. Okay. Let's consider a few results, a few conclusions of Newton's law of motion. So let's have a look at any material system. According to the second law of motion, we have that change in momentum, derivative from momentum of the whole material system. Is equal to sum of all external forces. And plus sum of all internal forces, I, and this will be doubled sum because we have two indices, and here of course key is not equal to I, because material point cannot act upon itself. So here we have F E I. And according to this Newton's third law of motion, we have this relation. According to this, we will get that this second sum of internal forces, it is always equal to zero. Because of Newton's third law of motion. So we have got law of conservation of momentum. 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 It is a generalization of second Newton's law of motion. Law of conservation of momentum. According to this law, we have such relation where this is sum of external forces. So it means that internal forces cannot change momentum of the system. So we have if this sum is equal to zero, if the sum is equal to 0, here we will have derivative equal to 0, and it means that momentum will be constant if when p momentum, which is equal to sum of momentums of material points of material systems, and this can also be written as mi vi, and this is equal to some constant. This is equal to some constant. This is equal to some constant. So this is a law of conservation of momentum. It is conclusion from Newton's law of motion. It is a conclusion of Newton's law of motion. And what is the last for today? The last for today will be the center of mass. Center of mass. What is center of mass? Center of mass is a point, a geometric point with radius vector. Center of mass. Center of mass. Center of mass. Center of mass is center of mass is point with radius vector RC. That is equal to sum mi ri, where ri are radius vectors of material points, and m mass of the whole system. So I can write where m is equal to sum of masses of material points. Sum of masses of material points. Or for rigid body, or for continual rigid body. For rigid body, rigid body consists of infinitesimal number of material points, and for rigid body we will get integral instead of sum. We will get integral instead of sum. RC is equal to triple integral radius vector r, rho in point r. Rho is density. Rho is density of rigid body. dV divided by m. And in the same way, we can write where m is equal to triple integral rho in point r. I remember that rho is density. And here this is definition of center of mass. And what is special? What is special about this point? What is special about center of mass? Let's find derivative from this radius vector RC. drc divided by dt which will be v c and the velocity of center of mass vc, and it will be, according to the first formula. If you use second formula, result will be the same. Mi d r I divided by dt and divided by m, and it will be derivative from radius vector is velocity. So we will get m sum mi multiplied by vi divided by m. But we know that this sum is a sum of momentums of material points. Sum of momentums of material points. We know this from here, that that it is equal momentum of the whole system. Is equal to momentum of the whole system. And from here we will have m v, and velocity of center of mass is equal to momentum of the whole system. Momentum of the whole system. And let's find another derivative, second derivative, m d v c by dt is equal to dp by dt. But according to the law of conservation of momentum, this derivative dp by dt is equal to sum of external forces. Is equal to sum of external forces. And F and sum of external forces. Okay, do you have any questions about this?
No, it's fine still. Mm-hmm.
Okay. And it will here we have proven the theorem of center mass motion. The theorem of the motion of the center of mass. Center of mass. Zoom said that is necessary to write center of mass. The word center should be written in this way. Okay, I think it is not make any difference. Let's will be written as this. Okay, that's enough for today. that's enough for today. I thank you for your attention. Thank you for your attention, and I hope to meet you tomorrow. I hope to meet you
Thank you,
tomorrow.
teacher. Mhm.
Okay, have a nice day.
Have a nice day, teacher.